Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework for lesson 101. All right, number 1, explain why the electrostatic potential energy formula, U equals K Q1 Q2 over R12, has a positive sign, while the gravitational potential energy formula, U equals minus big G M1 M2 over R12, has a negative sign. Well, there's nothing to really draw here, but I can say that unlike gravity, the electrostatic charge can be positive or negative. In gravity, like masses attract, but in electrostatics, the sign of the product for the two charges that attract is negative. So positive charges in positive electric fields move from high to low potential energy. Negative charges in positive electric fields move from low to high potential energies. Number 2, calculate the electrical potential energy of a hydrogen atom and compare it with the gravitational potential energy. Use the values below. And so I give you a set of values to use in the calculations. This is very similar to what we did in the lecture. Let me just go over it real quick. So let's calculate the potential energy, the electrical potential energy for a hydrogen atom. That's going to be K. Q, I'll write it as Q sub E for electron times Q sub P for proton over, we'll just write R for the radius of separation. So plugging in the values, we get 9 times 10 to the 9 times minus 1.67 times 10 to the minus 19, and that's of course coulombs, and that'll be times 1.67 times 10 to the minus 19 coulombs again, all divided by 5.3 times 10 to the minus 11 meters. And so if we plug that into our calculator, what we get is minus 4.7 times 10 to the minus 18 joules. Now a similar calculation for gravity, what do we get? Call it U sub GR for gravity, and that's going to be equal to minus big G, right, M sub E for mass of the electron times M sub P for mass of the proton divided by R. And this is equal to minus 6.672 times 10 to the minus 11, that's the gravitational constant, times 9.1 times 10 to the minus 37 kilograms, that's the mass of the electron, times 1.67 times 10 to the minus 27 kilograms for the mass of the proton, divided by 5.3 times 10 to the minus 11 meters. I'm just going to check something real quick. That's a funny coincidence, I think. Yeah, ignore the 1.67 for the charge here. I think this is just supposed to be 1.6, but I'm pretty sure that's what I typed into my calculator. Probably just a typo, me copying the mass of the proton for the charge. Anyway, so if we punch this into our calculator, what do we get? We get minus 1.9 times 10 to the minus 57 joules. That is a teeny tiny amount of energy. Okay, number 3. In problem 3 of lecture 97, we had the following configuration of charges. This is the charges in the 3, 4, 5 triangle. Calculate the potential energy starting with Q1 and moving each charge in one at a time. Recalculate starting with charge Q3, followed by Q2, and finally Q1. Okay, so we're just going to calculate the potential energy for this, and I'll just remind you of the configuration that we had. We had Q1, Q2, and Q3. And this was 3 units, 4 units, and 5 units. And we assume that they're all positive values. So let's see. Let's start with, we'll do the 1, 2, 3 ordering first. So the work for moving charge 1 in, of course, is 0 because there are no charges present yet. So there's no repulsion that they would feel as we tried to move new charges in. The work for 2, however, since charge 1 is already there, is going to be equal to K Q1 times Q2 over the distance between them is 3. And then finally, the work for charge 3, to move that in, has 2 contributions. We've got K Q1 Q3, and that's over a distance of 5. Plus we have K Q2 Q3, and that's over a distance of 4. And so in the end, the work, I'll call it work 1, 2, 3, is equal to K Q1 Q2 divided by 3 plus K Q1 Q3 divided by 5 plus K Q2 Q3 divided by 4. Okay, so that's the work to put it in the order first charge 1, then charge 2, then charge 3. Now let's work it out for 3, 2, 1. So we'll put it in exactly backwards to the way we did it before. This time, the work to move charge 3 in will be equal to 0, but the work to move charge 2 in will be equal to K Q2 Q3 over the distance between Q2 and Q3 is 4. And then finally, to move charge 3 in, we have 2 contributions this time. Oh, excuse me, not Q3, Q1. Q1. We have K Q1 Q2 over the distance 3 plus K Q1 Q3 over the distance of 5. Therefore, the work, W321, is equal to K Q1 Q2 over 3 plus K Q1 Q3 over 5 plus K Q2 Q3 over 4. And we can see this is exactly the same as the work to move it in the other order. So it doesn't matter what order we move the particles in, or the charges in, the work is the same and the potential energy is the same. Okay, problem number 4. Recalculate problem 3 using the formula, and there's the formula. And we're going to use n equal to 3. Okay, so I'll just work it right below here. I'll make a note that this was problem number 3, and this will be problem number 4. So, our formula for the potential energy, U, is equal to the sum of I equals 2. N is 3, so this will be a 3 on this sum. And the other part of the sum is J equals 1 all the way up to I minus 1. So that will depend on what our I value is. And I'm just going to write it as F of I comma J so that we can kind of get these terms out. So our first term will be F of 2 comma 1 plus F of 3 comma 1. And the reason we went to 3 is because after when I was 2, the upper limit for the J sum is 2 minus 1, or 1, so we only have the one term. Now our upper limit is 3 minus 1, so we'll go up to 2. So we get F of 3, 1 plus F of 3 comma 2. And those are the terms, and we'll note that F of I J is equal to K QI QJ over Rij. Okay, so now we can plug in the values for this. And so we get, let's see, K for F21, we'll get KQ2 Q1 over R21. F31 will be KQ3 Q1 over R 3, 1. And f of 3, 2 will be k q3 q2 over R 3, 2. But note that this is the same thing as, now I'm going to plug in some numbers for this. So we'll get k q2 q1 over, the distance between 2 and 1 is 3, plus k q3 q1. The difference between 1 and 3 is 5. And finally k q3 q2. And the difference between, distance between 2 and 3 is 4. So over 4, and we get the same thing that we got in problem 3. Okay, problem 5, assuming k equals 1 and q1 equals q2 equals q3 equals plus 1. What is the value of the potential energy from problems 3 and 4? So we can use as our base pretty much any of these. That's problem 5. We'll just use the last formula that we got here. So that's going to be U is equal to, well, since k is 1 and q3, q2, and q1 are all equal to 1, all of the numerators here are going to be 1. So that's just going to be 1/3 plus 1/5 plus 1/4. And now it's just a matter of, you could find the greatest common divisor for 3, 4, and 5. Or you could just do it one at a time. You do 4 times 5 is 20, and then 3 times 20 is 60. So we see that the greatest common divisor is 60. 1/3 plus, we get 4 plus 5 is 9/20. And now that's going to be equal to 20 plus 27 over 60, which is going to be equal to 47 over 60. And this would, of course, be joules if our charges were in coulombs. Okay, and finally, problem number 6. What is the potential energy if a fourth charge is inserted here? And so by here, it's pointing to this new location, charge number 4. It wants us to express as a multiple of the old potential energy, which is the potential energy we got from problem 4. But since we want to express it as the old potential energy, we may as well just use the numbers that we got, because that will allow us to get the new value in terms of the old. So problem number 6, so we're going to add the charge right up here. This will be Q4. The distance from Q3 will be 3, and the distance from Q1 will be 4. And of course we'll have this distance across here to Q2 will also be 5 by symmetry. So we'll use K and the charges equal to 1 again. And so we write this out, we'll get U equals the old charge, 47 over 60. Plus we have to move in all the new charges. So we'll have K, Q1, Q4, or Q4, Q1, I'll write it, over R 4, 1, plus K, Q4, Q2 over R 4, 2, plus K, Q4, Q3 over R 4, 3. I think I have all the terms. Yeah. And that will be equal to 47 over 60 plus, we'll have 1 over 4 plus 1 over 5 plus 1 over 3, which you can see is just simply 2 times U old.